Okay. Welcome to the session, Eurovis full paper session on applications. And it's my pleasure to welcome you all to the session. And I hope that you will enjoy this session with us. It's about 4 quite different papers, but they have something in common. Some of them relate to geospatial data. Some of them relate to other types of data with different reference systems. But all of them are very interesting, and I'm happy to introduce the first speaker. The paper is VA-TRACK, Geospatial Trajectory Analysis for Monitoring, Identification and Verification in Fishing Vessel Operations. The talk will be presented by Soya Storm-Furu, and the paper is together with Stefan Bruckner from the University of Bergen in Norway. My name is Daniel Keim, and I'm from the University of Constance. And I'm looking forward now to the presentation. And after that, we'll have the chance of questions. And the speakers are all online and will try to answer your questions. So enjoy the presentation.
We present VA-TRACK, a prototype visual analytics application for the monitoring, identification and verification of fishing vessel operations through analysis of vessel movement trajectories. The application was developed in collaboration with the analysis group at the Norwegian Directorate of Fisheries. Seafood is the second largest industry in Norway, with a fishing fleet of over 6,000 registered vessels. Since Norwegian waters, and by extension fish, are considered as a public resource, regulation is in place to ensure fair access and to ensure the longevity and sustainability of both the Norwegian fishing industry and the oceans. The Norwegian Directorate of Fisheries is the primary developer and enforcer of such regulations. Vessels are required to report the contents, duration and location of each fishing operation and to continuously report their position while on fishing trips. Over the coming years, the number of vessels required to report are slated to increase by an order of magnitude. In order to effectively uncover infractions in reporting, even with this increase in reporting vessels, the Directorate looks to partially automate the analysis process. Reports from fishing catch operations are inherently dynamic and may be influenced from a diverse array of factors, including but not limited to the fishing gear used by the vessel, weather conditions, the vessel's location, and the time of year. Analysis of reports therefore requires domain knowledge from a wide variety of sources, many which are difficult to model algorithmically. Additionally, the penalties for not complying with regulations can be harsh, including large fines and even jail sentencing. In order to ensure that decisions to prosecute a vessel can be explained, analysts must understand how decisions by automatic systems are made. This leads to a solution where a human analyst works in tandem with a computer. As common in visual analytics applications, VA-TRACK uses automatic algorithms that are used to analyze and filter the dataset before a human performs further analysis. In VA-TRACK, automatic algorithms indicate vessels that may have performed unreported and therefore illegal catch operations, after which a domain expert is presented these vessels for verification. In the parlance of the Directorate of Fisheries, classification algorithms that indicate whether a vessel may be performing illegal activities are called indicators. During the design of VA-TRACK, 3 such indicator algorithms were chosen in collaboration with analysts at the Directorate, based on the goals of transparency to allow analysts without intimate knowledge of algorithms to understand how classifications are made, evolvability to account for the dynamic nature of catch operations, and speed to allow analysis to occur interactively. The speed classifier determines when vessels are moving in speeds below a certain threshold, which often indicates that the vessel is fishing. The image shows a vessel's speed over time. The red dots are highlighted by the speed indicator and correspond to catch operations performed by this vessel. The K-nearest neighbor classifier uses earlier catch operations that have occurred around the vessel to determine the type of fishing gear the vessel uses. The movement pattern classifier exploits the fact that many types of catch operations lead to trajectories that have distinct shapes. The $1 recognizer by Wabrock, Wilson, and Lee, originally envisioned for identification of finger gestures on a smart screen, is used for this purpose. Previous catch operations are processed into pattern templates, and the recognizer is repeatedly applied along the path of each vessel's trajectory to find parts of the trajectory that correspond to the template. The typical workflow when using VATRAC follows the steps of identification of vessels that may have performed illegal operations, evaluations of the results from the indicator algorithms, and potentially a refinement of the indicators for more accurate future indications. The analyst starts by exploring all vessels that have been active in a time period, optionally filtering the group of vessels to explore by various parameters. When a vessel of interest is found, the analyst will filter the application to display only this vessel, temporarily removing the distraction of other vessels. The spatial and temporal dimensions of the vessel's trajectory are consulted to identify indications of illegal activities, which are compared to the domain knowledge of the analyst with the help of spatial and temporal views to determine whether the indications are correct. If the analyst sees a need for modifying the indicator algorithms, for instance due to the introduction of new gear types, they can optionally continue by changing the indicator algorithm parameters from within the application. Finally, the analyst would verify that the changes to the parameters do not come at the detriment of the performance of the indicators across all vessels. The following videos demonstrate the workflow of VATRAC. Since individual vessels can be identified in the application, their names and identification codes are blurred. The application consists of three views. The spatial dimension of the vessel's trajectory and fishing operations is shown in a map view. The temporal dimension is shown in a timeline view. Other attributes, including the vessel's registered and indicated gear type and name, is displayed in a tabular list. Catch operations are highlighted using a red and green color scheme. Reported catch operations are marked using green, while unreported and indicated operations are marked using red. The first vessel with a potentially illegal operation is selected, and the views are filtered to only display the trajectory of this vessel. The map shows that the indicated operation, highlighted in red, has happened while close to port. Likewise, the timeline shows that the indicated operation has happened while the vessel is nearly still. The indication is thus deemed incorrect. Another vessel has a plausible indicated catch operation. The timeline shows that the vessel has been moving slowly for a period of time, which has been highlighted by both the speed and movement pattern indicators, as well as looking plausible in the spatial dimension. Hovering over patterns in the movement pattern template viewer highlights the pattern both on the map and in the timeline. The earlier catch operations in the area can be superimposed on the map. Since the area seems to be a common fishing area, the vessel seems suspicious and can be flagged for further investigations. Due to the dynamic nature of fishery and to allow a gradual enhancement of the indicator algorithms, VATRAC allows the indicator parameters to be modified interactively. By enabling the model building mode, a line chart is displayed. Every time a parameter change occurs, sensitivity and fallout is calculated for the indicator algorithms and displayed in the line chart, giving users the ability to see the development of indicator performance over time. When enhancing the speed indicator, one identifies vessels where a catch operation should have been indicated using the timeline. A pop-up allows the analyst to tweak parameters for various categories of vessels. For each category, a histogram of movement speed during catch operations is shown, with a currently selected vessel highlighted. The histogram helps the analyst determine whether a chosen speed threshold is plausible. When modifying the threshold, the speed indicator is reapplied automatically, and the views are updated to reflect the change. Likewise, the indicator performance chart is updated with the sensitivity and fallout at each modification. For the K nearest neighbors indicator, the radius in which the indicator looks for fishing operations can be modified, again separately for different groups of vessels. The superimposed catch operations show the data point used by the indicator and are color-coded based on the gear used. The user can display circles with the radii to be modified, allowing interactive feedback when modifying the parameter. Modifying the movement pattern indicator involves constructing new templates based on the existing ones. The analyst selects templates with specific patterns based on domain knowledge. Each pattern is displayed in a larger view, with the average between each pattern highlighted. Certain templates have features that the analyst wants to be more pronounced in the average. These can be given increased weight. When satisfied, the template is stored to a database. Validation of VATRAC occurred through the use of two methodologies. Primarily, measures for validation were selected following the nested model of visualization validation by Munzner. Additionally, Elmquist and Yee's pattern for visualization evaluation was consulted when choosing specific methods of validation. In addition to qualitative feedback from group sessions, presentations, and individual interviews, a small-scale quantitative study was conducted in the form of a system usability scale questionnaire. We collaborated closely with the domain experts in the analysis group at the Directorate of Fisheries throughout the ideation, design, and development process, and received valuable contributions in both choices of the visualization design and in choice of indicator algorithms. The response from the domain experts was positive, and plans were laid to continue the development of VATRAC as well as to deploy the application more broadly in the organization. To summarize, we have presented VATRAC, a visual analytics application in a relatively unexplored domain, namely fishing operation regulation. Due to the fact that VATRAC was developed through close collaboration with domain experts at the Norwegian Directorate of Fisheries, we also learned multiple lessons about the collaboration between researchers and large governmental agencies.
Okay, thank you very much for the presentation. Now we have time for questions, and you can post the questions in Discord, the FP3 applications channel, or like here in the chat window of YouTube. Both is fine. I guess you can even talk in the Discord channel, and that could be put online. So let me start until the first question comes in with an obvious question about the application. We heard that it will be further deployed. What is the expected use? Is the expected use in saving time or finding more like violations, or like compared to the current state, or what is the expected usage?
So currently the vessels don't really get registered automatically. And there are a group of people called inspectors at the Directorate of Fisheries who travel around in the ships, like illustrated in the presentation, that need to somewhat quickly identify vessels that have performed illegal activities. And the utmost goal of the application is to help them quickly determine which vessels are actually have potentially performed the illegal activities, so that they can catch them kind of in the act, if you will. So its main goal is to speed up the process of finding vessels that have performed illegal activities.
Okay, thank you. We have 3 questions in the chat window in YouTube. So the first one is, do you know of databases of templates like the ones you used?
I am not sure if there are any templates available for fishing vessel movement patterns. one goal of the application, or at least one feature that was added, was the ability to construct such a database for the Directorate of Fisheries, so that they later on will have a good database of such movement patterns for the specific gear types for the vessels common in Norway.
Thank you. The next question is, can you please clarify how the data was collected?
Right. So the data is collected by the Directorate of Fisheries. They receive reports from each vessel every day, which the vessels have to send in manually. So they have to manually send their reports to the Directorate of Fisheries. That part, that's one part of it. That's the actual reporting, and there they need to specify like the start and end time of the catch operation. The other part is collected by the Norwegian coast authorities. And that's the movement pattern, the GPS coordinates of the vessel, and they collect those every 5 minutes. The data is then processed by the Directorate of Fisheries before it can be used by VEITRAC.
Okay, thank you. Final question that we have received so far is whether it's possible to search by vessel position in addition to pattern shape search, or is this simply not relevant to the end users?
I'm going to assume that vessel position search means the actual location on the map of the vessel. In that case, well, yes, you can navigate the map, so you can kind of search in that manner. But for many types of vessels, and many types of catch operations, they can occur very many different locations. So you wouldn't really use it to specify specific locations for specific types of vessels. But one use case I could see where you would want to zoom in on a specific location is when the inspectors are out at sea and they want to focus on the area where they currently are located. In that case, they will have to identify each vessel that are close to their area in the map view.
Okay. I see no more questions, so let's thank our speaker again. And we move on to the second presentation. Now we are moving from fishery to mobile phone networks. And mobile phone networks are, of course, widely available. And the paper is a collaboration between Brown University, Microsoft Research Cambridge and Redmond, and Tableau Research in Seattle. And the paper is entitled Orchard Exploring Multivariate Heterogeneous Networks of Mobile Phones. The paper will be presented by Philip Eichmann, Darren Edge, Nathan Evans, Bon-Chin Lee, Matthew Bremer, and Christopher White, and it's presented by Philip Eichmann.
People from all walks of life regularly interact with complex information networks that model the attributes and relationships of real-world entities. Examples range from media consumptions, such as video and music streaming services, books, and news, to job, school, and housing searches. The representation and analysis of complex information networks has a rich history in the fields of information visualization and visual analytics. Some of the proposed approaches employ faceted search interfaces in which users iteratively refine filters by selecting from prefabricated facets. In an application called FacetLens, for example, users can search large collections of research papers by specifying different facets, such as authors and their affiliations. Other applications, such as Orion, provide topology-based methods to support visual analysis of node link diagrams and adjacency matrices. and some use combined facet and topology-based approaches, as for example graph trails, where users can apply filters to sets of nodes of a particular node type and pivot to all connected nodes of a different type. While most of the proposed applications are primarily designed for desktop-sized displays, we posit that there is a significant demand to perform everyday network search and exploration activities on mobile phones. However, previously proposed interfaces have deficiencies when applied to multivariate heterogeneous networks on small screen devices. First, purely faceted interfaces do not convey the underlying heterogeneous network structure. They do not present how facets of nodes in a network or nodes themselves relate to one another, making it difficult for users to grasp the concept of pivoting between different node types. Second, topology-based approaches do not translate well to mobile phones where space is very limited. In this work, we propose a new list-based paradigm with gestural navigation of structured information spaces on mobile phones. We present a mobile application called Orchard, which combines ideas from both faceted search and interactive network exploration in a visual query language to allow users to perform complex network analysis tasks through a simple, easy-to-use user interface. The biggest challenge in achieving this goal is to expose the complex functionality required to perform common network analysis tasks through a simple UI. For instance, users need to be able to apply drill-down filtering, to pivot from intermediate result sets to associated nodes, and to apply data transformations such as network projections. To expose functionality in a compact way, we introduce an abstraction called pivot trails that we use in a visual query language to specify common network queries. Pivot trails are partial specifications of how a network is traversed and filtered. Let's assume, for example, we want to query a network containing information about films and related entities such as genres, characters, and people associated with these films. Every entity in the schema is multivariate, meaning that every node type has a set of attributes. Suppose we want to find all films related to a particular topic. To do so, we define the query as directed acyclic graph that schematically encodes the topological constraints as linked node types. Each node type can have an arbitrary number of filter constraints or facets, in this case the topic name MI6. Since the two nodes are directly linked in the schema, the pivot trail fully defines the network query. Let's now look at a slightly more complex example. Suppose the following. Of all people associated with MI6 whose name is Judi Dench, we want to find all associated films. Here is the fully inferred specification. The compact pivot trail hides the actual complexity of this full specification. While the previous pivot trails show linear sequences or lateral pivots, they can easily be turned into drill-down filters or a combination thereof by restructuring the links. To showcase how this applies to a gestural navigation, let's move on to a quick demo. The attribute exploration view can be used to configure a bar chart-like list of nodes. Nodes are grouped by some attribute, in this case the film title, and aggregated by another, for example, the count of distinct topics. For instance, here I choose to sort the list of film titles by the number of associated people or by the number of distinct films per title. To change the grouping, I can tap the Group Pivot switch and select an attribute or node of interest. Here I group all film nodes by their release year, showing how the number of released movies has evolved over the past decade. With Orchard, users can search across all attributes of any node type in a network by using the keyword search. Let's say we're interested in finding all James Bond films. Intuitively, we would select the film title attribute. Yet doing so reveals that there are only 2 movies with James Bond in their title. Alternatively, we can try to find Bond films through the character named James Bond. To verify that this is the real James Bond, I switch the aggregation pivot to film, which tells me that there are 19 connected films. I can now pivot to the 19 Bond films by selecting the character and by swiping left starting on the film tab in the pivot bar. Upon completion of the gesture, a new group pivot is added to the pivot trail. This interaction can be repeated an arbitrary number of times to blaze a trail through the network. Here I'm now interested to see a list of people associated with Dr. No. But which of these people played James Bond? To answer that, I can reuse previously selected items as facets to filter the current list by tapping on their corresponding link icon. Nodes in the pivot trail can be deleted through the context menu or by dragging them out of the trail. Furthermore, tapping on the Details button at the bottom reveals detailed information about the currently selected nodes. Detail views can be customized. In this case, Orchard will redirect to the corresponding Wikipedia page. By default, Orchard matches any of n selections when pivoting to a different node type. For example, when selecting 2 films and swiping to person, all items shown in the list are linked to any of the previously selected films. If instead I wanted to find only people that appear in both films, I can change the match mode to all through the context menu. To do this type of comparison for any combination of films in the current list, I can swipe left again on films. Doing so computes the co-occurrence or co-linkage of some other node type per film combination. For example, common people, topics, or characters. The generated combination can be used just like any other facet. To validate the design of Orchard, we conducted a lab study with 12 participants in which they were asked to complete a set of predefined tasks as well as to explore a movie dataset on their own. Participants were immediately comfortable navigating back and forth by swiping left or right. Swiping on a related entity to pivot was reported to feel natural and intuitive. We observed that the number of nodes in a pivot trail during exploration can grow rapidly. Various participants pointed out that it would be helpful to be able to store intermediate results by collapsing a subtrail into a named pivot. Finally, while our query model hides the complexity of queries that involve multiple hops, some participants mentioned that exposing the computational path on demand would help users gain a better understanding of the network's topology. We presented Orchard, a mobile application that uses a novel query model to facilitate a simple user interface design to explore multivariate, heterogeneous networks. Using our approach, minimal user input is required to formulate common network queries. Given the ubiquity of information networks and the encouraging feedback we receive from experts and lay users, we see great potential in providing a mobile solution for casual browsing of richly associated datasets.
Okay, so thank you for the presentation. So I would like to start again with one question. The question is whether you have any other applications in mind. This was a very specific application, but I guess your collaboration partners certainly have other applications in mind.
Yeah, absolutely. So we tried this out on a number of different data sets. So the system is set up so that you can plug in any network data sets. And so we played with different ones. For example, we're mostly interested in more casual data sets. So for example, soccer statistics, job and house searches, and so forth. So we tried a bunch of different ones, but chose the film movie data set to testing and evaluation just because it was easy. It was pretty easy to find people who are interested in movies and in films. Yeah.
Okay. We have one question here in the chat window. Who are the intended users? Was it hard for users to learn the several features interactions?
Yeah, so the intended users are really kind of like casual users. So rather than actual, analysts who have maybe a background in visual analysis or in analysis in general, we're targeting mostly users that don't usually use visual analysis tool per se, but would be interested in exploring their own private data or data that they use for like their hobbies or maybe in a job on a more casual basis. So the intended user are really people who just pull out their phone maybe on the bus or sometime at home in bed and so forth. And maybe the second question was it hard for users to learn the several features? It really wasn't. So certain aspects were extremely easy for people to learn, it seemed. So for example, I mentioned this in the talk, the navigation concept of being able to swipe back and forth just seemed very natural because there's other applications that follow the same principle. And then there were some features, for example, the network projections that required users to kind of like trial and error a little bit. But because the system is very lenient in terms of allowing users to actually make mistakes and revert back to a previous state, it didn't seem like a big obstacle.
Okay, we have another question. Do you have any ideas on how to extend this method if the network is dynamic, means changes over time?
No, we haven't really thought about this too much. Not in that line of work, but that would be an interesting question to address in a future version.
Okay. I also have one question. In your study, what did you get as feedback concerning, like, could you measure anything with respect to performance, or is that like just informal feedback?
So we were mostly looking for qualitative feedback because it seemed like this kind of technique is sort of new especially for mobile phones. So we're mostly interested in more qualitative feedback, whether or not people actually are encouraged to explore an information network they might be a little bit familiar with. We did collect some more like quantitative feedback as well, more like try to figure out how much people actually liked it, how long it took them to accomplish a set of predefined tasks that we set up for them. But for the most part, we were really looking for more qualitative feedback to see whether or not people would imagine using an application like this on their own data rather than just the movie data set.
And are there any plans of Microsoft or Tableau in putting it into any commercial application?
I don't think there's like a concrete plan to put this in a commercial application as of now. But I left Microsoft a few years ago, so I can't speak for them, I guess. Okay, I don't see any other questions on Discord or in the chat window, so let's thank our speaker again. And we will continue with the next presentation. The next presentation is Occupado, visualizing location-based counts over time across buildings. Now we moved from C to phone networks or heterogeneous networks on mobile phones, and now we are in building space. And the paper will be presented by Michael Oppermann, and it's joint work with Tamara Mansner from University of British Columbia. We are looking forward to the presentation.
Our design study Occupado. This is joint work together with Tamara Mansner. Understanding how spaces in buildings are used is a key challenge for decision makers and facilities management. But understanding occupancy by physical counting is too labor intensive, and installing hardware sensors is often too expensive. Previous attempts to visualize occupancy and other indoor sensor data are limited to very small regions such as single rooms or floors and relatively short time periods. In a multi-year design study, we engaged with many stakeholders to design, implement, and deploy Occupado, a set of visual decision support tools that use Wi-Fi occupancy data. Our collaborator, Sensible Building Science, collects Wi-Fi device data as a proxy for estimating human occupants. We save these location-based counts every 5 minutes and generate a time series for each zone. Zones are predefined spatial regions that are used to count devices. These can be, for example, research labs, classrooms, or office groups. We collected data from hundreds of zones across dozens of buildings. Our university campus served as a perfect testing ground with different types of buildings. The data is stored at regular intervals, every 5 minutes. An advantage of this data type is that we can easily aggregate zone-level counts to floors or buildings. No trajectories or device identifiers are recorded. We just know how the number of devices change over time, which leads to significant privacy advantages. Our industry collaborator uses Wi-Fi data to dynamically adapt heating, ventilation, and air conditioning in building management systems. We suspected that this data could be actively useful for decision-making and resource management. Previous studies and also investigations by our collaborator showed that Wi-Fi connections can be used as a proxy measure for occupancy. We don't get precise head counts, but we know if a space is empty or very busy, or for example if a space is only used for one-off events. Our goal was to understand the tasks of potential stakeholders in facility planning and operations. We conjectured that this data can be actively useful for certain tasks, but is not appropriate for others. For example, when it's important to see movements or highly accurate head counts. After a series of interviews, we identified stakeholders in 5 domains: space planning, building management, custodial services, classroom management, and data quality control, because Wi-Fi sensing is a fairly new approach and our collaborator uses Occupado to verify the collected data. We had multiple rounds of engagement with each stakeholder. All sessions involved semi-structured discussions interleaved with live demos of our prototypes. We identified 4 high-level tasks across all stakeholders. Confirm assumptions or previous observations. Do students always occupy a specific room in the evenings or on weekends? Live monitoring. Which rooms are empty or busy? Communicate and justify. For instance, to prove that usage of an informal learning space improved after renovation. And in addition, use Occupado to verify if the recorded device counts are correct. Our original assumption was that we would design different interfaces for different stakeholders. But instead, we found a significant overlap between stakeholder needs, and the questions could be captured by looking at different slices of space and time. The main regions of interest are zones, floors, and buildings. Depending on their questions, users are interested in different time periods: only weekdays, every Monday, Friday mornings, etc. In some cases, users want to see device counts over time to identify trends and patterns, but in other cases, measures need to be aggregated, for example, to see the average daily utilization. We started our design process with a sandbox for idea generation and prototyping. After getting a better understanding of stakeholder needs, we created the Campus Explorer, a feature-rich system that is connected to a live data stream, followed by 3 applications targeted to specific data granularities. The same stakeholder might use different interfaces for different tasks. Constraining the data dimensions allowed us to significantly reduce the complexity of the building long-term, building recent, and region comparison interface. Our target users are not professional data analysts, and ease of use was a key requirement. I will now show you a short demo of these interfaces. The Campus Explorer has three main components: the control panel at the top, the region select on the left, and the region subset view now showing Spark lines. Users can choose between multiple visualizations depending on the intended task. We implemented 6 different region subset views. We can click on a region to open the detail view as an overlay. A key component is the bin time series chart, to show device counts over time at different levels of detail. Initially, the confidence bands around the average line are wide, but the further we zoom in, the narrower they get, until the dark blue line represents the actual device count and the bands disappear. The Campus Explorer has many different views and filter options. To better support recurring tasks, we provide activity presets. These are shortcuts for complex interactions. For example, to show the regions with the highest device counts in the spatial heat map. We can filter regions by building, switch to different views, like superimposed line charts, or use temporal filtering. We select the week and days as discrete time sessions, and inspect a specific day. The built-in recent interface focuses on short-term data, with circle symbols size-coded by live device counts in each zone. On the left, we see per floor counts from the last half day, plus a future prediction. Or we can switch to see the average activity for a typical day. We can also switch the symbols from live data to the maximum over the past half day, or for example, to today's average count between 7 and 11 AM. In the building long-term interface, on the left we can select multiple zones across different floors. We can switch between spark lines to see trends over time, and average day profiles to analyze the typical utilization of a region throughout the day. Zones are sized to fit on screen. In the Region Compare interface, we can choose a specific region in a building. Select a time, like June to August, and see its time series. We'll pick September to December for our second query, and see both results superimposed for direct comparison across all the charts. We could also change the query to compare different regions. We created reusable visualization components for different data granularities that we can add to various Occupado interfaces like Lego bricks. I will briefly highlight the region subset views that we used across all interfaces. We use spark lines to show long-term trends, patterns, and outliers. In some cases, users are only interested in non-contiguous time periods, for example only Mondays. Boxplot bars show aggregated device counts for each time slice. Line charts with confidence bands are used to summarize the typical utilization, to answer questions such as, when do people usually leave on Friday evenings? And because aggregation can hide important details, we also show individual line charts superimposed. These 4 visualization components emphasize temporal aspects. In addition, we use floor plans with superimposed symbols and spatial heat maps to provide spatial context. Over the course of this project, we deployed Occupado tools for the UBC Vancouver University campus and Cisco's Innovation Center in downtown Toronto. Our industry collaborator adopted the visualization system as a front-end for their Wi-Fi data collection platform and is promoting it to customers and partners. Please have a look at our paper for a detailed discussion of our design decisions and for generalizable design choices for visualizing spatio-temporal data relating to indoor environments. Go to our website for supplemental materials, videos, and talk slides.
thank you very much for the presentation. We have time for questions. As always, you can post them in the Discord channel or in the YouTube chat window. Let me start with the first question. I just learned that the data provider is also collecting or wants to use it as an interface. What other applications do you have in mind? Because the application was very specific to the university setup, or is this similar in companies or other environments?
It would be very similar in other buildings or in company environments. We use the university campus because we have many buildings here, different types of environments, and it's very well connected with access points, so that's very important for the data quality. But every other company or every other building with Wi-Fi access points would work too.
Okay, so we do have some questions here. Do you think this can be used for contact tracing and social distancing?
We spent quite some time to make sure that it's a privacy-preserving architecture and that you cannot track individual people. So, for example, for COVID-19, it cannot be used. We don't know who is in a building. We only get rough estimates of the number of devices. And then based on the number of devices, you can make some assumptions how many people are in a specific lecture room. If there are only maybe 5 people, or if there are 50 or 100 people in a room.
Mm-hmm. Okay, so the answer was no, right?
No.
Okay, then we have a question. A gym with music has more noise than a quiet library. How do you consider this information in the tool to normalize the sound?
We're not using sound. It might affect the triangulation, but I don't think so. We are just using the Wi-Fi signal strength, and we've used different types of room settings, large lecture halls, and small office groups, and we got very similar data.
Okay, so when I looked at the interface, I thought it doesn't seem that easy to use. At least when I saw the video, I was thinking, oh, a new user, like I was thinking about the people in my university that are using the room planning and room usage. I think it would still be too hard for them to work with it. What was your experience?
At the beginning, we had a similar experience when we started out with different types of prototypes. As this persons, we want to add a lot of features. We want to provide many options to explore the data. But we quickly figured out that they are more interested in kind of getting reports, getting quick overviews of the data, because they were really interested in the data that they had no access to it before. So we started to split it up into smaller prototypes, simplified user interface, and especially the building long-term, building recent, and the region compare interface. They are they're focused on very specific tasks, and so they were much easier to use for them, and they really liked it. The Campus Explorer has a lot of features. We used it together, but it's tricky to get started. We created together activity presets, so you can directly jump to a specific view with different specific filters. This was one solution to the problem, to reduce the complexity and to make it easier for day-to-day use.
Mm-hmm. We have another question. You said that the movements between the locations have been omitted due to privacy issues. However, have you started to think about possible extensions for this aspect?
Not directly. We really didn't want to focus on movements because it was not relevant for our stakeholders, and I think we can address many questions without tracking the movement. I mean, there are a lot of privacy issues. We would need to get a very high level overview of movements or flows, but so far we haven't looked into it, but it would be a very interesting future work, I think.
One more technical question, like what do you think is the most interesting technical innovation in the tool? Like it looked quite adapted to the use case, but is there anything that is technically innovative in a sense?
We really tried to build this reusable components so that we can build prototypes extremely fast. So I think this is a good software practice, and I'm sure other tools do it too. But very often we see that people work on a very big, large system and then deploy it, and it's very difficult to make changes. And we tried from the beginning, already, to build these components, and then we can stick it together and quickly create many, many different types of prototypes.
Okay. I don't see any further questions in the chat window and in discourse. So last chance for that. Then I would thank our speaker again and move on to the final presentation. Now we are back in geospace and we are going to see a paper on crime hotspot analysis. The paper is entitled "A Visual Analytics Approach to Facilitate Crime Hotspot Analysis." And the paper is by José de Queiroz, Manuel Santos, Credo Vidal, and David Ebert from Brazil and Purdue University. And José is presenting the paper.
Hello everyone, my name is José de Queiroz. I am one of the authors of the paper A Visual Analytics Approach to Facilitate Crime Hotspot Analysis, which we would like to present to you. This is a joint collaboration with Emanuele Santos and Credo Vidal from Universidade Federal do Ceará in Brazil and David Ebert from Purdue University, USA. Crime is an important subject to study because of its cost to the society. Huge financial losses, physical and emotional harms are among the problems that crime brings. One of the most important players in the fight against crime is the police, an entity that in recent decades has been criticized as being expensive and ineffective, but they are trying to change their strategy. For example, they've been trying to change from a reactive posture to a more proactive one. They are leaving random patrols to use scientific analysis, and they've been trying to reduce the number of officers. Some new techniques are now common in police departments, like community policing and problem-oriented policing. These two techniques are supported by hotspot policing, a technique that recommends identifying regions with a high concentration of crimes and the deployment of more resources there. Two important areas among police activities are criminal analysis and resource allocation planning. Both activities would benefit greatly from analysis based on hotspots. For these activities, police officers generally only have overly technical and time-consuming systems at their disposal, which ultimately leads to modest use. In our paper, we show other related approaches and discuss how they not fully meet the domain tasks and requirements. In our approach, we worked with 2 police departments in the USA and 1 police department in Brazil in order to identify a set of domain tasks that would have a significant impact on police operations and to develop a visual analytics solution named SHOCK, the one-shot comparison tool, to address them. In the paper, we also included 2 different real-world case studies to demonstrate that our system effectively supports the completion of the domain tasks. The domain tasks were defined based on observations of the police officers' meetings, where we identified the questions during the internal discussion of the problems. We checked and adjusted the findings through later interviews. So, let's see the domain tasks and the questions that have led to them. The first domain task is hotspot identification and comparison. It consists of identifying priority areas of relative importance, the hotspots, and comparing pairs that represent different periods. The questions involved in this task are: where are the hotspots? Where were the hotspots? What is the priority now? Should our resources move or stay? How much of our resources should be moved? The second domain task is hotspot evolution. It consists of tracking the hotspot over time using an absolute level of likelihood. The questions related to this domain task are there hotspot expansions? Are there hotspot contractions? Are there new hotspots? Are there hotspot disappearances? Are hotspots moving? How to evaluate an intervention? The third domain task is the multi-time analysis. It consists of identifying how crime is distributed in different periods of the day. The questions officers use to ask are: do hotspots expand, contract through the day? How does the crime vary in the shifts? The fourth domain task is the multi-type analysis. It consists of identifying how different types of events correlate with one another spatially. Typical questions involved in this task are: is there a correlation between drug abuse and thefts in this region? Where to place specialized teams? Where to place mixed teams? The fifth domain task is the multi-level analysis. It consists of identifying regions based on increasing levels of likelihood. The basic question is: how many resources should be allocated in each part of the city? During our 2-year collaboration with the police departments, we developed a visual analytics system that provides an interactive visual environment for encouraging data exploration. Users can visualize crime events in different ways, such as point maps, choropath maps, and density maps, KDE and MSKDE. The maps are organized in layers and can be made visible or invisible using the layer control. Those maps are fully configurable. For example, the users can control color and transparency, point size and shape, line borders, etc. Also, our tool includes spatial and temporal filtering components for selecting the dataset to be analyzed, and an annotation component which enables users to annotate their findings and plans directly on the map. When officers started using our system to perform the domain tasks, we noticed that they spent a lot of time to complete the comparative analysis. Some spatial comparisons would sometimes take a lot of cognitive processing from the users. They would build separate maps and make computations inside their heads. After a careful analysis of the domain tasks, we identified that they would benefit from a surface comparison tool. So we developed a novel technique called SHOC, the one-shot comparison tool, to make hotspot comparisons in a more direct way and avoiding this cognitive overload. Let's see how SHOC works using as an example a multi-time analysis to see how crime is distributed in different periods of the day. Initially, the user selects the first dataset, choosing the type of event, the date frame, and the events that happen in the day. On the MaskAD component, the user sets the parameters: the cell size, which is related to the resolution and performance of the map, the bandwidth, which is the influence range of each incident, and the percentage of density, which is how much crime density will be included in the map. After plotting the first layer on the map, the user selects the second set of data, choosing incidents that happen at night. The other parameters are kept the same. Eventually, the user can change the color of the layer to provide better contrast. The user then presses the SHOC button and starts exploring the map. New layers were automatically added to the map. They can explore the map using the layers individually or in groups. As we can see, MSKDs can be superimposed with minimal occlusion, displaying immediate spatial variations to release the user from making any visual comparison. Everything is integrated into one frame, including hotspots, the base map, and annotations to facilitate printing and taking pictures. The system displays the difference and intersection of hotspots in a familiar OIL diagram form to aid handling and interpretation. Stable regions are shown in solid light yellow polygons, and regions that experience changes are shown fully transparent with their original border. Similarly to the given example, we have identified combinations in parameters and datasets that help to solve all domain tasks. We will demonstrate that SHOC helps to perform the domain tasks in 2 real-world case studies. In the first one, we worked together with the Lafayette Police Department and the Purdue Police Department to track drug abuse in Tippecanoe County, USA. The police knew that the recorded number of drug abuse incidents was increasing, and they wanted to know more about how and where that increase was taking place. We performed Domain Task 1 and Domain Task 2. Based on the Domain Task 1 analysis, we could identify that from 2016, shown in blue, to 2017, shown in red, drug abuse is more concentrated in the downtown part of the city of Lafayette. Notice that the number of incidents almost doubled from 2016 to 2017, but the hotspot area decreased. The concentration is also confirmed by the increase in the threshold, meaning that the crime likelihood level on the red border is more than twice that on the blue border. Thus, we can conclude that crime increased and concentrated in 2017. Additionally, based on the Domain Task 2 analysis, we could recognize that areas with at least the same likelihood of the hotspots of 2016 expanded in 2017, and new hot areas appeared. The second case study shows an analysis of homicides and robbery in Brazil. In the DT3 analysis, we could identify significant differences in the distribution of robberies between the morning, shown in blue, and around noon, shown in red, when the hotspot moves from Zone B, a less developed area, to Zone A, a richer one. Officers have used the DT4 analysis multi-type to plan an intervention to prevent homicides and robbery. They defined it and annotated using the system the green polygons as areas for patrolling from 6 p.m. to midnight. The DT5 analysis shows the crime density regarding homicides at two levels, 25% and 75%, to give indications about progressive resource allocation. The domain experts' feedback about our approach was in general very positive. Officers expressed excitement with the possibility of comparing on the same screen hotspots of different time frames or different kind of incidents. They considered that shock would have a positive impact on routine activities and that the annotation layer would improve communication and teamwork. They also made suggestions to improve the tool, such as to simplify the interface regarding the number of input parameters. Some of the limitations of our tool are with respect to input parameters. Officers have to set cell size, bandwidth, and the density percentage, which is not natural for some of them. Shock also computes polygons operations, such as intersections and subtractions, for two MSKD layers, and the resulting pairwise comparisons satisfy the requirements of the officers. In our experiences with them, visualizing more than 3 MSKDs at the same time is not recommended because of clutter. In this video, we showed a characterization and abstraction of the hotspot analysis problem into 5 domain tasks and presented Shock, a tool that facilitates performing the domain tasks by giving a straightforward way of making spatial comparisons using set-like operations on superimposed geometries. We demonstrate Shock effectiveness in 2 real case studies that helped police departments on planning their preventive initiatives to fight crime. This was only a brief overview about our approach. Please read the paper for more details, and thanks for watching.
Okay, thank you very much for the presentation. Again, we have time for some questions. You can use Discord or the chat window to ask questions. And before the first question comes in, let me get started. You said that you applied it in some use cases. Is this an everyday use, or is this like in a pre-stage, or what is the status of the software?
In the United States, it was we have used it in a few meetings, but in Brazil, this software has been adopted by the Ministry of Justice, and they refactored the system, and we are deploying it all over the country. So it's used currently in production in about 12 states in Brazil at this moment.
Okay. Is it also used in the US?
I don't think so, because when we left the USA, they were started to use, but without being together with them and giving training lessons. I think they are not using anymore at this moment.
Okay. So please ask questions on YouTube or on Discord. We are still able to get them done. Let me ask another question before the first question comes in. What is the most interesting technical contribution of the work? It's very nicely applied to the application domain, to the use cases, but what would you consider the most interesting technical contribution?
We think that the visual comparison of two hotspots in the same screen, the same font, this possibility of comparison, spatial comparison, is a good contribution, because we can compare variables of different magnitudes, and we can give to the user instantly in a contrast about the hotspots, and releasing them to make any visual comparison. The users don't need to make any visual comparisons. The comparisons are already done for them.
Mm-hmm. Okay, we have a question now. When you give people crisp polygons that represent uncertain, dynamic, continuous phenomena, is there a danger they will overinterpret?
I'm sorry, could you please repeat the question?
Sure. When you give people crisp polygons that represent uncertain, dynamic, continuous phenomena, is there a danger they will overinterpret? Like, is what you show is actually something that is very uncertain, continuous. It doesn't have crisp boundaries, and you describe them by crisp boundaries. Is that maybe dangerous for the application people?
You mean about the border?
Yeah, you have a clear boundary. It's like a polygon that you show, and the phenomenon doesn't end there. It's like continuously.
I understand. On. Okay. The boundary, the border is really the officers love that boundary, because the border gives to them information that is very easy to interpret. So it's very difficult for them. We've noticed that sometimes it's difficult for them to analyze a hotspot without a border, because it's the hotspot using KDE, for example. It's just an image, yeah? So they usually it's difficult for them to interpret and make comparisons. Using the borders, we give a clear information for them. We give the percentage of density that is inside the border, so they know what is surrounded by that border. So it's for them to compare, and it's the only way to not the only way, but a good way to put in the same screen 2 or 3 hotspots and facilitate comparison of that phenomenon.
Mm-hmm. Yeah, we have in the chat the comment that shapes look like things, but surely they are pretty arbitrary, and a comment that it's a threshold of the distribution. So you basically have a distribution of points that give you a continuous distribution, and of course you put in some boundary of the distribution in order to get these crisp borders. Any further questions? What do you think are the next steps?
Well, we are using the system to track other phenomena, not only crime. Our state is using this system to track the coronavirus. They are tracking the phenomena because the system is good for making comparison about variables of different magnitudes. So it's not only good for dealing with crimes. For example, in the United States, they have made a very interesting analysis about comparisons between crash cars and car crashes and traffic stops. So they could verify if the traffic stops are following the car crashes. That in the United States. As I have said, we are using to track coronavirus. It's very interesting to to see the evolution using 2 or 3 polygons showing clearly where the coronavirus is spreading. It's very interesting.
We got another question. What are the possible limitations, if any?
There are some limitations. The first limitation is the number of layers. The user, we've noticed that starting from 4 layers or more, it's difficult to interpret the map because of the clutter. And another limitation is about the parameters. The user has to set the cell size, bandwidth, and the density percentage. And it's not natural for some of them, so we have to give training sessions about these variables. But we're trying to change the strategy regarding the parameters, creating profiles for the municipalities and profile for their users, because it's not necessary for the chief of the police to know details about parameters for kernel density estimation. I think it's not necessary for them, but some officers they like the technique, and they like to know about them. So we are planning to create profiles where certain profiles will use parameters, or the profile you use only consume the analysis.
Did you experience, like in your usage, any reduction in crime, or what? Like, is there any measurable impact that you achieved?
I think it's too early to say that. But I can tell you that the officers they like the system. They like the way the simplicity. I love QGIS and ArcGIS, but sometimes it's too technical for them, and they love the simplicity, the easy access to the data sets, and to create the hotspots. And even after creating an analysis, they like to take pictures with their mobile phones, and that's the appeal of the system. It's very simple to use.
Okay, I see no further questions in the chat nor in Discord, so let's thank our speaker again, and we conclude the session unless there are any questions to any of the speakers. If there are any question to any of our speakers, if that is not the case, and I see nothing coming in, let's thank all of our speakers again, and then we conclude this session. Thank you very much for attending.
Thank you. Thank you very much.